In this video, we will prove the fundamental theorem of calculus. That's a theorem that gives you a way of calculating area under curves using antiderivatives. It's a very powerful way of doing that, provided you can actually find an antiderivative. If all you want to know is how to use the theorem, you might as well skip this video and move on to the next one, which explains how to use the fundamental theorem of calculus. We have already proved that the area under the curve is a limit of a Riemann sum. Let me remind you of that. So this is the example we've seen before, and that's a GeoGebra animation that shows what's happening. So we want to find the area under the curve, that's the yellow area, so we could use Riemann sum that use the left end point of the interval and get that, or the one that use the right hand point. And what happens is that if you increase and increase and increase the number of sub-interval, then the Riemann sum will get closer and closer and closer to the area under the curve. And doing that is really taking the limit as the number of sub-interval goes to infinity. We will now prove that a change in an antiderivative is also the limit of a Riemann sum. And so if these two things are equal to the same one, then they have to be equal. And that's exactly what the fundamental theorem of calculus says. And after that, since really using the Riemann sum is much more complicated than using antiderivatives to find area under the curve, we'll mostly forget about the Riemann sums. Now that we have a strategy, let's get started. Say you have a small change in x, called delta x, like here, and you want to express the corresponding change in f. So that's the graph of your function f. Well, if your change is really small, it turns out that the function and the tangent line are almost the same. So if we zoom on this part of the drawing, we get that. So the blue curve is the change of f, so delta f, the change in f really is this. If delta x is small, this side of the triangle using the tangent will be very close to the change in f. The reason why you want to use the tangent is because you know that the slope of the tangent line is rise over run, and that gives you a way of calculating what you want. Now the rise is almost equal to the change in f, and the run is delta x. If you multiply both sides of this equation by the change in x, you're going to be getting that if you multiply the derivative by the change in x, this is really close to the change in f, which is what you were trying to evaluate. We now know how to evaluate a change in f caused by a small change in x. This is what we got from the previous slide. Now, how would you evaluate a change in f caused by a large change in x? For example, how would you evaluate f of b minus f of a? The idea is to divide the interval ab into small sub-interval such that on each of them this formula is valid. Let's do it. Let's label the points on the x-axis. In order to find the total change in f, which is this distance, what I could do is calculate this small change, and that one, that one, that one, that one, that one, and just add them. So let's start with the first one, and since it's the first one, let's call it delta of f1. This change in f is caused by this change in x when x goes from x1 to x2. So according to our previous formula, there, the change in f on the interval x1, x2 is going to be f dash of x1 times the change in x, which is really, in that case, that's really my x2 minus x1. I'm assuming that this interval has been divided on sub-interval of equal length, so any of these will be called delta x. So delta x is that, but it's also any of the other one. Now let's do the same thing for delta of f2, which is there, and which has been caused by the change from x going from x2 to x3. Using our previous formula again, this little change in f can be obtained by taking the derivative. So in that case, I'm assuming that the tangent starts from the left-hand point. So I'm using f dash of x2 times delta x. And of course, I can do the same for all the other subinterval, delta of f3, f4, f5, f6. Now that we have added all of them, we indeed get f of b minus f of a. It's going to be easier to recognize something, not telling you what, if we just do a change of notation. And we call the derivative of capital F little f. Also, in order to help you recognize something, instead of writing delta x, I will write h. Hopefully, you'll recognize what I'm writing down now. You've seen this before. And there are some hints somewhere on this slide. Do you see it? The hint is there. We're trying to see a Riemann sum. And actually, if you look at that, that's exactly a Riemann sum. Let me draw something that could be the graph of f, because we don't know exactly what f looks like. Maybe here. And let's say it's increasing. If that's x1, and let's say that's x2, this first term here, h times f of x1, will be the area of that rectangle. And in that case, as I said, this is y is equal to little f of x. The second term, we will get this one, will be f of x2 times h, that's f of x2. And we're going to be getting this second rectangle. So what we get here is a Riemann sum. It's the Riemann sum of little f over the interval AB. Now if we take the limit as the number of subinterval approaches infinity, so these subintervals are going to get smaller and smaller, so this approximation is going to get better and better, and we're going to have more and more rectangle under the graph of little f. So the Riemann sum of little f over AB will get closer and closer to the area under the curve of y equal to little f. So that area. And this is exactly the fundamental theorem of calculus. So what we have shown here is that if you have a function little f and it's positive, so that's what its graph looks like, and you're interested in the area and the curve between a and b, this area is actually equal to capital F of b minus capital F of a, where capital F is an antiderivative of f. And that's a wonderful result because it gives you an easy way of finding the area under the curve. Just find an antiderivative, then sub in b, sub in a, and subtract, and that's it. So thank you for watching this video, which explains where the fundamental theorem of calculus comes from. In another video, we'll learn how to use it.